the bistable states. And well, so a little bit about this presentation. We are going to be working first, like talking about the motivation for this work. How this works? Okay. Some motivation, like why we did it, why to study the ionic channels, etc. And then the methodology, the models that we have been using, the tools that we use for measuring synchronization, the burst to spike to burst transitions and other things. And then also, before going for those ionic channels, a quick analysis of the standard Hodge-Huxley model that will be talking about sodium and other channels. And then we go to the bistable regime that appear in the network, talk about the calcium effects, and then conclusion, some other projects that we have been working on, and some references. So first, why study this? Like, it's well known there are many works that have shown that epilepsy and abnormal synchronization is related, is a dynamical disorder in the brain that is characterized by the abnormal synchronization of burst activity. And well, and also another thing that are related to it is the bistable states and also the multi-stable states that can appear, mostly in the transition from spike to burst. And well, and since like there is also some activities in the brain that are related to like all activities that we do, that is the ionic channels. They are the main reason why neurons work. So understanding how they work, what they are doing there, if they have some triggering into those epileptic seizures, it's very interesting for also so that we can tackle new types of treatments using maybe focus on some type of ions or different concentrations, and also may get some new mechanisms underlying the seizures. And well, so how did we do it? First, we use a conductance-based model that is, well, a fancy name for a Hodge-Huxley-like model that is described by like these equations here. Well, there is way more equations for each neuron. It's around 9 equations and way more parameters. And well, and the standard Hodge-Huxley model, it works only with those two ionic channels, the sodium and potassium current. And in the model, we want to study the dynamics of slow potassium, the IM, and those two here are related with the calcium dynamics into the neuron. And well, we worked with cortical neurons from humans, and it was random network that we use, the Eidos-Reni network, where there was present inhibitory neurons and also excitatory neurons, and well. And then some tools that we used was like the frequency of the network, how they were firing the entire network, the coefficient of variation, the CV, that is a matrix that can tell us if the network is in spike activity or burst activity, depending on the values that we have here. And also to measure the synchronization, we use the Kuramoto order parameter for the global synchronization on the network. And well, so first, a quick analysis of the standard Hodge-Huxley model. If we have a network composed only of Hodge-Huxley's model, excitatory, inhibitory, if we vary the values of the input currents that we use in each neuron and the coupling strength, we can get different dynamics. We can get like synchronization of spikes, desynchronization of spikes, high frequency, but we cannot find burst activity or like synchronization of burst because the Hodge-Huxley model is not able to capture this type of dynamics since in a single cell, when we are talking like a single cell of Hodge-Huxley, the only way to get burst is when we introduce the calcium dynamics. Since this channel is like one of the main, has a great role into the burst activity. And here, those three here is like the voltage trace of just a single neuron of Hodge-Huxley. In this case here, we implemented the calcium and slow potassium, then we can get this initial bursting, and also if we change some parameters, we can get like full bursts into the network. But well, so if we think calcium has like a great role into this burst activity, we may think, okay, if I include this into a network, I'll get burst, synchronization, etc. So this is like something necessary. And well, we have observed that no, to get those bistable regimes and also those type of burst synchronization in a network, it's not necessary calcium. The only current, like the minimal current necessary, is the slow potassium current that is related with the slow dynamics of some potassium channels. And here, we have like a parameter space again from the external input and the coupling strength. And this white region are the bistable regions, the bistable states that we can observe. And they are in these regions here of the transition from the spike to burst. And well, and also here we have those big regions of burst synchronization that are way related with the seizures. Here in those 3 panels, we can observe better here the hysteresis curve from this region here, from those dots here. That when we start with asynchronous states on the blue triangles, it will stay in that dynamics for longer, for more couplings. But if we do the opposite, start with high synchronization of neurons, this will stay for other values of coupling, we will get those synchronization of burst. What is very interesting, because like even though the slow potassium has a great role into the adaptation of the neuron, since they have a slow dynamics to open and close during spikes, it's very interesting that when we couple many of those neurons, we can get those rich events of burst activity. And well, so calcium has a great role in burst. And what will happen if we implement this into the model? Here, we have a parameter space, for parameter space for different conductance. So in this first case, we just have slow potassium. When you can get those regions here of bistability, that we need like some coupling greater than 0.8. But now, if we include the slow dynamics of calcium, what happens? We get this panel here, where there is if we observe here, it's a larger region of bistability. But if we increase a little bit more the external input, we don't find anything. There is just like spikes appearing, not more bursts. But now, if we have just the high threshold calcium dynamics on this panel, the bistability is facilitated. Like if for more values of coupling, for values of external input, we can get easier for those bistable states. But now, if we have the complete model, what happens? We get kind of intermediate state from those two here that it's facilitate here the bistable states. And also, we don't need like too much coupling, that it starts like from values below 0.8 that we can get those burst synchronization. And just a few conclusions here, that like in a single cell level, the Hodge-Huxley, it's not able like to produce the burst activity unless we have calcium dynamics. But when we are in a network, the potassium plays a great role into that. And also that the calcium has an influence in facilitating those states. And this is very interesting because if we're thinking some methods to suppress those synchronizations, we can aim for some type of specific channels so that we can get like new results, understand a little better how the epilepsy works and seizures. And well, this work was published in Brain Science 2023. Here, like if you're interested, there is like also the QR code. And there are many more things that we did, like we studied a little more into the ionic channels too. And well, and here are some other projects that we have worked before, and like there are some still in progress, that we work like with intermittent states of synchronization in the cortex and other brain regions, some oscillations as spiral waves, chimera states, also some delays and other bistabilities. And then also some other people there, we work sometimes with like some epidemiological models and like some plasticity. And I want to thank everybody here, the organizers, the event here, the group that I work on, and then some references. And that's it.
Thank you. Thank you, Diogo. Questions, comments? Yes.
How do these, do you know how this parameter landscape compares to empirically measured values for this parameter? These bistable regions, something we expect to see considering real values obtained empirically?
Like, you mean like the parameters from the model? That you mean?
The Hodgkin-Huxley model is very biophysically inspired. I mean, it's almost a direct consequence of how the biophysics works.
Yes.
So most of these parameters, they may be measured in a
Yes.
lab. Where do real parameters fit into this parameter landscape?
Oh, okay. So those real parameters, like, well, it's not here like all the equations here. It's way more parameters, and all the parameters that describe each of those currents, they have been experimentally measured and even described. So, like, all the parameters that we consider here are like for cortical, the cortical neurons from a human. I don't remember the age of the human, if it's male or female too. But we have like all the parameters that we have is like experimentally measured, and also the conductance here. For example, here, these are the conductance of those channels. We are using some from papers. I don't remember the papers there, but they set those values that are like representing the real activity of those neurons.
One more question.
Okay.
Thanks, Dio. So I have a question from, it's maybe a naive one, but so in your model, this I input is a stochastic process, I guess. It's like some noise that you put in the system? Or?
No, in this case, not. It's just it's a steady current that goes like in each neuron receives this steady current. If we get like some noise, these like some bistable regimes appear yet. Of course, like sometimes it's shifted a little bit, but if we increase too much the noise, like it breaks everything. It's mostly desynchronization.
So I guess my question is, if you look at the distribution of inter-spike times in all these different regimes, how do they look like?
Well,
I guess,
yeah. No, I got it. Like, so when we have like those activity of burst, they have like a very particular shape. The easy distribution, like if we get, like they have those, how to explain it? They have like a peculiar shape. Even like you can change like the parameters are a little different on the values of x or other things, but they have like particular shape. Like they look like a L more or less. They appear in the distribution. Like if we have like easy n plus 1, easy n, we have the distribution. They have a particular shape.
Thank you.
Okay.
Okay, so let's thank Diego again. Now we change subject.